The mathematics of blast furnace top gas composition and efficiency. Over the next few minutes, we are going to move beyond just looking at top gas number. We are going to learn how to interpret them mathematically, how to turn those percentage into actionable insights about what happening 30 meter down inside the furnace. By the end of this presentation, you will have a new set of tools to help you listen to what the furnace is telling you and make better, faster decisions. So let's start with a core concept. We often say that top gas is the furnace voice. It's the primary way the process communicates its internal state to us. Take a look at this typical top gas analysis. We see CO, CO2, nitrogen, and hydrogen. These are not just a random number on a screen, they are the coded message. This mixture tells a story about everything happening from tier to stock line. What kind of story? It tells us how efficiently our most expensive raw material, coke, is being used, or whether the crucial chemical reactions, the reduction of iron ore, are proceeding properly. If permeability problems are starting to develop, that could lead to a furnace slowdown or a hanging, and it can even tell us when the cohesive zone, the heart of the furnace where softening occurs, is starting to misbehave. Our job today is to learn how to decode these messages. So, how do we start decoding these messages? We use a couple of simple but incredible power mathematical ratios. Think of them as a furnace vital signs, we can say. The first and most important is the gas utilization factor, or eta CO. You will see the formula here, eta CO is equal to, it's understood and it's known to everyone, so I need not to talk more about exactly this. The both ratio, the gas utilization factor and CO CO2 ratio, but still let us try to revise. You'll see the formula is eta CO and percentage CO2, percentage CO2 divided by percentage of CO plus CO2 multiplied by 100, and eta CO, at its heart, this number tells out all the CO that was available to reduce iron ore, what percentage actually succeeded to turn into CO2. So it's a direct measure of the efficiency of your gas. The second indicator is your CO2 ratio, as it is mentioned here. Uh, it tells you how much gas was used. This tells you how much gas passed through unused. Uh, a high ratio means a lot of rich unused gas is exiting the furnace, which is a sign of inefficiency. We'll see how these two work together. Now we are coming to formulas. Now that we have the formula, we need a benchmark. So what do this number actually mean? This table gives us a guide. Look at the relationship here. Excellent efficiency, that is above 50 or around 50 eta CO, correspond to a CO2 ratio of less than 1.0. That means you have more CO2, the product of reduction, than CO, the unused gas in your top gas. So that's the sweet spot. As the efficiency drop, the eta CO number falls and CO CO2 ratio climbs. A ratio between 1.0 and 1.2 is still good. Between 1.2 1.5 is the average. Between 1.5 and 1.8 is poor, and anything above 1.8 with eta CO below 35% signals a serious problem in the furnace. So we are essentially wasting or reducing gas and our coke. Keep this benchmark in mind. It's your reference for the healthy furnace. So let's bring this to life with a real world comparison. Here we have data from the two different ship A and B. On the surface, B looks impressive. They have 24% CO in their top gas, which is higher than shift A 21%. But don't be fooled. Let's do the maths. We calculate data CO for shift A, and which is coming round for shift A is 50% and for shift B 42%. So excellent efficiency. Now for so this is only the average range. The key insight here is a crucial one for all of us. High CO in the top gas is not necessarily a sign of good operation. It can actually be warning sign. Shift A is a better performing shift because they converted a higher percentage of their available CO into useful work of producing CO2. They use their gas more efficiently. Never just look at one number in isolation. So, where does this CO2 actually come from? It's created by the chemical work of the furnace. Let's look at the mathematics of reduction. As ore descent, it goes through three main steps. First, hematite reduces to magnetite, then magnetite to straight, and finally the critical last step was straight to iron. So look at the equations in every step for every molecule of CO that does its job. We get one molecule of CO2. Think about the scale of this. Mathematically, for every 1 kilogram of iron we produce, we have to remove around 0.5 kilogram of oxygen that was originally bonded in it. To remove that much oxygen, you need lot of CO, and that chemical reaction generate approximately zero point 0.7 normal cubic meter of CO2. This is the fundamental link between your production rate and your gas composition. When you see CO2 in top gas, you will literally see the footprint of the reduction work your furnace has just accomplished. So this is where our maths gets really interesting and operationally critical. So let's introduce a concept called solution loss reaction. This is when CO2 instead of exiting the furnace react with a hot coke to form to CO. So look at this table on left. We have a ideal furnace without solution loss. We start with 100 unit of CO from the tuer. It does its work producing 50 unit of CO2. The top gas end up with a balanced 50 units of CO and 50 unit of CO2, giving us a unhealthy 50% data CO. Now look at with solution loss column. Here 20 units of that newly formed CO2 goes and react with coke. It consumes 20 unit of CO2 and create 40 unit of new CO. So what happens to our top gas? Final CO jumps from 50 to 90. So final CO2 drop from 50 to 30, and our eta CO crashes from 50 down to 25. This is most important lesson in this presentation. When the solution loss reaction kicks in, CO increases but CO2 decreases, and eta CO drops dramatically. It tells us that our precious carbon is being wasted on gasification, not used for reducing ore. It's a sign of thermal inefficiency and potential coke degradation. So now let's look at a practical example from an 8,600 ton per day operated blast furnace. This is an real shift data, and let's walk through the numbers from 6 a.m. to 2 p.m. Notice the trend at 6 a.m. to CO is 22.1 and CO2 is 20.5, giving us a good data CO of 48. Pressure drop delta P is stable at 1.5, and our wind volume is 8250 normal meter cube per minute. But as the shift progresses, watch what happens. CO is climbing from 22 to 24. CO2 is falling from 20 to 18. Consequently, eta CO is dropping all the way down to 42 only. And critically, delta P is increasing while our wind volume is decreasing. What does this swing tells us? The diagnostic is clear. The solution loss reaction is increasing, CO2 is reacting with the coke creating more CO2, which is why CO is up, but this reaction is endothermic. It consumes heat and degrades the coke. The degraded coke is hurting permeability, which is why we see the pressure drop, go up and struggle to push wind. This is a classical sign of furnace under thermal stress. Now coming to our mathematical interpretation, the CO increase scenario. So we saw CO increase wherever you see that you have to ask why did CO go up? It's not always bad, but you must do the math to find out. Here are three possibilities. The good scenario, the more reduction work is happening, but in that case CO2 should also be up. Your delta P should be stable and your eta CO would stay the same or even improve. Bad scenario 1, solution loss is increasing. This is what we saw in our data. CO is up but CO2 is down. Eta CO drop and delta P increases because the coke is weakening. Bad scenario 2, that is channeling. This is where the gas finds a path of least resistance through the burden bypassing the ore. Here CO would go up or CO2 would go down and eta CO would drop, but you would likely see a drop in delta P as the gas find an easy way out. So let's apply these mathematical tests to our data. CO is up, CO2 is down, eta CO is down and delta P is up. So this doesn't match the good scenario or channeling scenario. It points directly to bad scenario 1, solution loss. And finally, let's look at the other side of the coin. A decrease in CO2, just like with a CO increase, a drop in CO2 can have a multiple root causes, and the surrounding data helps us pinpoint which one. Which one? So first, a CO2 decrease would mean less oxygen was removed from the ore. This is simple. Reduction has slowed down. If this is the case, we need to check our burden quality, our temperature profile. Are we getting the heat we need into the stack? Second, and this is one we have focusing on, it could mean more CO2 is being consumed by the solution loss reaction. The oxygen is still being removed, but the CO2 produced is immediately eaten up by coke. We have already covered the implication for coke rate and permeability. Third, a drop in CO2 would mean the gas is bypassing the ore zones entirely in a channeling scenario. Here the gas simply doesn't come into contact with the ore to form CO2 in the first place. So to summarize, by the applying simple mathematics to our top gas analysis, calculating eta CO and CO CO2 ratio and analyzing trends in the conjunction with delta P and wind volume, we can listen to the furnace voice accurately and diagnose its internal state. This is how we move from reactive operation to proactive and efficient control.